And this time we're going to talk about formal semantics. A pretty interesting topic for me as well. Again, I have to say that I'm not a professional in this area with years of experience, definitely not. So I may say something stupid today, specifically on this lecture. So feel free to judge me with enough skepticism, so I may be wrong. But I'm going to tell you how I understand this, how I understand this territory of dealing with programs. So this is the structure of the lecture. So we're going to talk about the rules, the axioms, and trees. So this is like a quick introduction of the things which we're going to deal with. Most of you probably understand them, but I will still recap our knowledge there. Second, we will discuss the difference between operational and denotational semantic. Actually, we're going to discuss what is semantic in general, and then the difference between operational and denotational. This difference is hard to, it was for me hard to understand from the literature and from the videos of other people, but it seems that I somehow built some understanding, and I will share it with you. Then we're going to discuss natural semantic, which are denotational, and the structural semantic, which are operational. And you will see the difference. Then we'll discuss reduction semantic, and finally some literature for you to take a look at. So what is in general semantic? What does it mean, the word semantic? We already have the lexer, we have the tokenizer, then we have the parser, and then after the tokenizer we have the abstract syntax tree. After the tokenizer we have concrete syntax tree, then we have abstract syntax tree. Now we look at the program, and now it's time to explain to us, me to you, you to me. Let's say we're programmers, we're designing the language, so we need to communicate to each other. What does it mean? Let's say the program is let's say my program is 5P7. So this is my language, and I made this language. So I'm designing, now I'm trying to tell you how my language works. And I will tell you, my language, my grammar of the language is this. The command is the argument, the operator, and then the argument. I would even say this: the argument, the T, and the A. Right? Okay, and then I will tell you, A is a number: 0 or 1 or 2 or 3 or 4, 5, etc. And the T is P or M. All right, clear? It is clear. The syntax is clear, right? Everything is good. But we don't know what the hell does that mean. It's just syntactically correct program. But what do you do with that? I mean, what does it mean? 5P7. The syntax is right. The concrete syntax tree can be built. So we can say, okay, this is the command. The argument is 5. The T is P. Here is P. There is 5. Everything's cool. But what does it mean? Nobody knows. So now we need to somehow explain what do we mean. We need to say that, what P actually means plus. So the result should be 12. And say, so you meant plus. So this P actually has a meaning. And the meaning is semantic. So the word semantic is meaning. So by means of semantic, you explain what was the meaning of this letter P. Because syntax cannot explain that. In the syntax, this information is not presented. So now we will discuss in this lecture how you can explain to other programmers, to other people, the meaning of your syntax. So what is the P? But let's start with the instruments we're going to use. And we're going to use 3 things: rules, axioms, and trees. So first of all, inference rule. Again, maybe some of you already know this, maybe from other courses, but I'm still going to recap it. So inference rule. A proof system is formed, these are the quotes from Wikipedia. So a proof system is formed from a set of inference rules chained together to form proofs, also called derivations. Any derivation has only one final conclusion, which is the statement proved or derived. This is the way rules are written. It's called inference rule. It means that what is true on the if what is on the top is true, then the bottom is also true. So let's say I can say if the weather is fine, I go to forest. So if the weather will be true, then I go to forest. That's a primitive example of an inference rule. If something is true, then what's at the bottom line stays, will also be true. And there is a name of the inference rule. Sometimes on the left, sometimes on the right. It's just a name which stays in the rule. Sometimes people even add the condition on the right side of the inference rule. Sometimes we can see, and we will see the rules like this, which may look like this. They say, okay, skip it. I'll explain it later. I don't know what I can't find a right example. So what's on the top, what stays on the top, it's called premises. And what stays on the bottom, it's called conclusion at the bottom. What stays on the top is usually called also facts. So it's something which we know is a fact. And what's on the bottom is the new fact we generate. And this symbol, it's called, what's the right name? Forgot. So this symbol means that it stays there. Well, usually it means the full syntax is that some environment, let's say that means that if this is based on this, we conclude, we derive this, we derive the information B. So based on this A, we can say that B is true. So based on the information that, for example, let's say based on the thermometer, based on the thermometer, based on the measuring device, we can say that the weather is good. And based on, and then we go to forest. So this is like the source of the information for us, the source of this fact. But if we don't put any source here, then it means that it's like the fact which is not necessarily based on anything, it's just a fact. So we're saying if A is less than B and B is less than C, if these two facts are available, then we can generate another fact. We can say that A is also less than C. That's the idea. So they're called antecedent and consequent. What's on the top, what's at the bottom. And what's at the bottom is in only one. So on the top we can put many things. We can say the weather is fine, I have money, I have the bicycle, and then I go to forest. So there are three premises and only one conclusion. Conclusion may only happen once. So we can only have one conclusion, but many premises. Or zero premises, which leads us to the axiom. Axiom is an inference rule where there is nothing here. So there are no premise. So for example, like I can say, my name is Igor. So I don't need any premise for that. That's just a fact which we know for a fact. It's an axiom. So whether I go to the forest or I don't go to the forest, that's a different story. That's something which is based on, which may happen or may not happen. But this is 100% fact. So if we have a fact, then we just draw it like this. We just don't put anything on the top. We also can give it a name. And at the bottom we say, for example, x multiplied by 0. Of course, it's going to be 0 no matter what, in any situation. So we can read, it reads, in any environment, pay attention, any environment. So on the left here stays nothing. So it means that no matter what, in any environment, in any, based on nothing, it's just the result of multiplication of x by 0 equals to 0. And previously, yeah, and inference rules, they read like I told you before. Based on this, we may conclude then that. And finally, transition rule. Interesting part, which we're also going to use to discuss semantics. A transition rule defines the conditions under which a system may be moved to a new state. So that's a classic example. So on the top we say, by the way, what is the system? The system is something we deal with. It's it could be a machine, it could be a computer, but usually it's some system which runs, which works, and we're trying to explain the semantic of this running machine. Like before, I told you the 7p5, so I was trying to explain you the semantic of some calculator. So that is the system. So transition rule is trying to, by using transition rule, we will we do that. We define the conditions under which the calculator, the computer, which is staying in one state, can move to a different state. What should happen to it? Maybe the command P should be given, and then the computer will do the arithmetic operation addition and save the result into memory. So by the transition rule, we explain that. We can say, basically, we can say, if you see 5p7, save 12 to memory. This is our very primitive semantic of the calculator. And if I give you this semantic, this inference rule, then you will know how to implement the calculator. But basically, I'm not going to tell you 7p7. I will tell you, if you see this abstract syntax tree, where you will see the command, and you will see 5, and you will see p, and you will see 7, then save 12 to memory. Or maybe even better, I will tell you, if you see p with 5 and 7, then save 12 to memory. Or maybe even better, I can say, if you see p, x, and y, then save z to memory, where I will make a note for you in this inference rule. I will add some information to the rule here, like a comment, and say where z equals x plus y. Just a note for you. So now I perfectly explain the semantic of my calculator. I give you the premise. This is called premise. And then here I give you the conclusion. And with the marker, with the comment, which gives you more information about what's going to happen. And this plus here will tell you how to implement the calculator so that it understands the problem. So the rule, the inference rule, usually has a form like this. On the left side, we say, on the left side stays in this angle brackets, we say some command, like what's coming into the machine, and then we say state, in which state the machine is right now. So let's say the command P is coming, and in the state we have nothing, so machine is empty. The command, not the P, the command P57 is coming, and inside the machine we have 0, nothing, so it's empty. So this is my situation. This is my input, and this is my state, input or command, something which I'm getting in. And then I say the transition. I define the transition. So in this case, here stays the transition, and here stays the transition. And the inference rule says, if the transition on the top is possible, then the transition on the bottom should happen. So I'm saying and the transition is the move of the system from one situation to another situation. Let's say in this situation we nothing, so the command is gone, so no input anymore. But here we say that in the memory we have map to 12. So this is my state, which is a map, which is a map of key value pairs. So I saved the new variable, the new memory, the new element in the memory. I saved 12, and nothing is there anymore. So the input was there, the input is gone. The input was coming, the input is gone. But the state was empty, now the state has something. So that's the transition of a system, of the transition of the computer, which is a system. Let's read the rule which is here on the screen in front of you. Let's read what it says. So the rule says at the top, if an input to the system is variable is a, the letter a, and if this and some state, so if the calculator is seeing the letter a and it is now in the state s, if the transition to a different situation may happen, and in this different situation, instead of a, we will see n. If from the letter a we can make n, and let's say n is the number, the natural number, then if this is possible, then a plus plus, if we see a plus plus, then we can transfer it to also n, but the state will change. Inside the state we will save the new value by the name a, and the value will be n plus 1. This is exactly how the x++ operator works in C++. It sees the x++, it knows, for example, that x is 24, so it reads this. After this, if you, for example, do this, then in the end you will get y will be equal to 24 and x will be equal to 25. So it will update the memory, but will return 24 to the x. So we just explain this logic, explain this semantic in one inference rule, non-ambiguously, because this was just a explanation on the intuitive explanation. I just intuitively explained it to you, like with the numbers, 24 is coming, 25 is going out. It's just intuitive explanation. This is the formal explanation. I'm saying that if you can transfer a to n, then a++ will be also transferred to n, but the state will be updated. Is it possible to remove this completely? That was my question when I was studying that. Was always my question. So can we write it like this? A++, we move it to n, s, a, n plus 1. We can do this. It actually says the same. It actually says the same. But it doesn't, if we do it like this, if we just remove and make it an axiom, then we will not be able to stack those transition rules into proof trees. And I will show right now what is the proof tree. Let's say this is a collection of inference rules for a programming language. This is the entire semantic of a language. Everything. So everything you need to know about my programming language is written here. Let's try to look at this and understand how the language works. So first rule is an axiom. The first inference rule number 1 is an axiom. It says that if you see x, then you just go to the state, to the memory, and take the variable from there by the name x. Simple as that. So if you look at the syntax and the syntax says x, then it means you need to read from memory and replace this x with what you found in memory. The second rule, if you see n, you just do nothing, you just stay. If you see n, and we assume that n is the number. So if and by the n we denote numbers. So if you see number, let's say you see in my language, I don't know, 42, then don't go anywhere. 42 means 42. So stay with it. So don't do anything. Just understand it as a number. That was the rule number 2. Rule number 3. If you see y, then and this y, you can move the system when you see the system with the state, when you see y in front of you, and you can transfer this system to n, so y is understandable as a number, then x, this syntax, x equals to y, when you see this string, this syntax construct, then you just remove it, so skip it. Skip means like, I mean, remove it from the processing, from the input, remove it from the processing pipeline, and change the state by setting x to the number n. So basically, if you see this, a, for example, a equals to 42, then this rule will be suitable for you, because look, a is, in our case, a is x, and y, is it possible to transfer y to n? So y is 42, so it is n. So that means we can update the memory. The next rule, rule number 4, we say if you see the command 1, actually let's read it from the bottom. So if you see command 1, semicolon, command 2, then you can transfer it to number, and the state will be changed 2 times. So it's state double prime. If, with 2 premises. Premise number 1, if the command 1 can be transferred to skip, and changing the state will be changed. And then you can take the command 2, provide the change state from here, and it will move it, it will transfer to the result to the number. And the state will be changed the second time. So basically, if you write a equals to 5, b equals to 7, then this is a perfectly fit for this rule, because this will be parsed by, these 2 elements, this is going to be C1, this is going to be C2, and they will be interpreted by these 2 transformations. So these transformations, they don't transform it, they just say it is possible to do the transformation. So when we say what goes at the bottom of the inference rule, this is what we want to do with the system. What goes on the top, it is what we think somebody did before. So it is what happened before, and if it happened before, then this will happen now. It's like if you put the gas into the car, then we drive. So we cannot just say we drive. We say if the gas is in the car. The same here. If x is transferable to number, then when we see the command which does with something with this x, then we manage this s, and we manage this x and do something with it. So basically, you can write it in a simple form. You not necessarily need these lines. You can say it like this. You can say if x is number, then x should save x into memory So this is basically the same, but less readable. I mean, it's readable maybe by a human being, it's more readable, but if you design more or less complex languages, and if you expect more or less different people to understand what you write, then there is a notation which people are used to. So this notation, more or less everybody will understand from the community. So if you design your language, if you want to publish a paper about it, if you want to do some, if you want to do it in a more or less scientific way, then you do it like here on the right side, not like on the left side. Because on the left side, it's more like a manual, like a documentation about the programming language. If you open the documentation about Java programming language, you're not going to see this. They will not give you that. They will give you this. They will give you intuitive explanation. They will say, you know what, when you do equals, then equals means this and that. And if you put the square brackets, then it means this. And they will give you examples. They will give you a long description of that by example. And you will understand it. You will understand it actually faster if you're a programmer than you would understand this. Because from this, you need some time to digest it, to really process this data and really get the meaning of that. However, the beauty of this format on the right side is that it is much more strict. So you cannot have double meaning here. Well, if you design it right, of course. You can, of course, make mistakes as well. But if you don't make mistakes, if you make this formal definition of the semantic, then the chances that you are understood unambiguously by another reader are much higher. Because when you write it on the left, you need to use the plain English, and in plain English, it's very easy to say something which has many meanings or double meaning. So that's why people decided to use the inference rules. But actually, it's exactly the same. The semantic is the same. These are interchangeable description of what's going on. But on the right side, it's more like it's something actually a computer can understand this. You can put the analyzer, which will just analyze this semantic description of the semantic of the program. It will tell you what it understands about the program. It will tell you what it knows now about how the program works. And now proof tree. I promised you that there is a necessity for this transition rule. So why they exist? Why we write? Sometimes we write quite silly axioms. For example, this one. So why we need this one? N to N. What's the meaning of this? It's quite silly from N to N. It does. And for example, like this one, this Y to N, also not always necessarily understood from the first sight. But there is a technique which is called a proof tree, where you can stack these inference rules one on top the others in order to prove that your program works the way you want it to work, the way you promised. So here's the title. Let's prove that this program equals to 6. It's not maybe obvious immediately because why it's 6, but I can prove it to you right now using the inference rules from the left side of the slide. So the program, I mean, let's maybe start from intuition here. So first of all, I assign A to number 5. And then I do A+++++. Those of you who understands C++ will definitely understand that the result will be 6, because A++ first will increment 5 to 6, and then will return 5. The second result, and then will return not 5, will return itself. And the itself will be 6. And then 6 will be incremented by 1 and returned 6. So in the end we have 6, but in memory we have number 7. Of course. So the result of the evaluation of this program will be 6, and the memory will be, in memory will stay 7. 6 will be returned to the user, and not to the user, but this expression, this entire expression will be replaced by 6. But in memory, we will keep number 7. And here's the proof. The proof starts from the bottom. So at the bottom, we say that, this is our entire program, this command, semicolon command, that the memory is empty, nothing in the memory, and we say that transition will happen, so the 6 will be returned, and in memory we will keep 7, just like I promised you, 7 and 6. This is my promise, now I'm trying to prove it. I go up. From this line, I say that what is the rule? Let's give the numbers. 1, 2, 3, 4, 5. So I'm saying, what is the rule I can apply to this situation that it will give me some premise which will lead to this conclusion? Because this is a conclusion. Now I'm asking myself, what could be the premise or a number of premises which led me to this conclusion? Like my conclusion is I go to the forest. But why do I do this? What was the premise? The premise was I have the bicycle and the weather is good. So in the set of inference rules, I need to find this rule which will help me to prove. I will say, you know what, in the rules I said before that when the weather is good and I have a bicycle, I will go to the forest. Now I'm telling you, I go to the forest. You're asking me why? I say, because the rule number 17. Look at the rule number 17. It says 2 premises, 1 conclusion. I have the conclusion, so I got it from the rule 17. The same here. So which rule is suitable for this? The rule number 4. I put it here. So I use this rule. The rule number 4. The rule number 4 says, if you have 2 commands separated with a semicolon, then if you have 2 commands, you can transfer it to the number n if this transition is possible and this transition is possible. So what do? I put these transitions here. My first transition and my second transition. And I say, this transition I also claim. I still trying to prove, so I'm going from the bottom to the top. I also claim, look, it is possible. A equals to 5 with an empty memory can be transmitted to skip, like nothing. We just remove this command, so we eat it, and we don't do any processing, and we save to memory A as 5. A is saved to 5, but A equals 5, and this is probably wrong because this is not skip. So instead of skip, we should say, because A with 5 is not going to return skip, it's going to return 5. It's going to return 5. Oh, there's a mistake. And sorry, it's equal. Sorry, my mistake. So that's right, skip. We just equal. We just save 5 to memory, and nothing is returned to the user. So we claim. I just claim that this is my another conclusion. So I say, let's say I go let's get back to our primitive example. So I say I go to forest, and you ask me why, and I say weather good, and I say bicycle exists, and then you say and then I say weather is good, but you ask me, are you sure? How do you know the weather is good? I say temperature is above 15, temperature is below 30, let's say this way. Hold on. So this is another logical derivation, as they call. This is my I go to forest. That's the conclusion. I made this conclusion because I had 2 premises. And then the question is, how did you make the conclusion that the weather is good? I had 2 premises. The temperature. The bicycle exists. How did you make this conclusion? Let's say it's an axiom. It's a fact. So the bicycle exists. It always exists. It's a fact. So I don't need any premise for that. It's a fact. So this is axiom number 1. This is the rule number 2. This is the rule number 1. And then the question is, the temperature is above 15 and the temperature is below. How do you know? I check the thermometer. I check I don't know. How do you know that the temperature is above 15 and the temperature is below? Let's say it's also the axiom. So it's a fact. We just know it. That's the reality. So this is the axiom 2, this is axiom 3. And this is the proof tree. So I go to forest because the weather is good because. So you always go up, answering the question why. We do it exactly the same here. So we'll look at this conclusion at the bottom and we find two premises. The premise number 1, premise number 2. And these premises, for them, we also find the right rules. So this was the rule number 4. This is rule number 4. What is the rule for this? When we say a equal to 5 and goes there. So how do we know that a equal to 5 will be, we can apply this transition? Okay, we have the rule number 3. The rule number 3 says that it is possible to do it with one premise. If 5 can be, if what's on the left can be transferred to what's on the left. And in order to prove this, we use the rule number 2, which is an axiom. And when we stop, there's nothing in here. It means the proof tree just stops going up. So no more reason to ask the question why, because we hit the axiom. And the same happens here. This is the plus. What is the rule? The rule here is rule number 5. And this is rule number 5. And this is rule number 8 of 5. This is rule number 1. So we used all the rules, 1, 2, 3, 5, 4, all of them. We used them in the proof tree. Stacking them up, one on top of the other, in order to demonstrate that the conclusion at the bottom is grounded by the rules on the left part of the slide. That's how proof tree works. That's how you can stack inference rules one on top of the other, demonstrating and guaranteeing that what you need is your conclusion actually does make sense. Okay. I hope it's clear, but it may be not so clear, but just try to stick with try to always remember the more simple example with the bicycles, with the weather and all that stuff. Because the way people write those rules and the people use these notations, it's very chaotic sometimes. So you open different papers and people use different notations. So it's better you just always keep the high level understanding of that the rule is just, they're trying to move you from what was possible at the top. It leads to the enabling the possibility of what's on the bottom. If something on the top was apparently is possible, then okay, what's at the bottom is also possible. And now let's go to operational versus denotational semantic. There are two ways, two possible approaches to describe the semantic of a language or programming language. The first one is denotational semantic. Denotational semantic, again, it's from Wikipedia or something. The denotational semantic assigns semantics, I would say semantic here, assigns to every expression the number denoted by that expression. So this is the symbol which is used in the transformations when we describe denotational semantic. For example, you say x with the n, the power n, goes to y, where y is x multiplied n times. So this is the expression which you can see in when the denotational semantic is used, and we try to explain the meaning of a program using that kind of a semantic. So all our transitions, and they happen in the inference rule. We're always going to use inference rules. So something stays on the top, something on the bottom. So here we explain the transition from here we say that we can transfer x, we can transfer it to, let's do it this way. Yeah. let it be x like this, if, and then something will happen on the top. I don't know what. Denotational semantic is the way to explain the meaning of a program by transferring from the program syntax to the data domain. This is what this expression means. So this symbol, this relation, belongs to the relation. It actually is part of the relation between this is the all expressions of our language, and on the right side all possible data. So we move from, if this belongs to A, this is the part of the language, then Y should be the data. So we always explain how this syntax, how this expression in the text can be mapped immediately to the number, to 42, to 3, to 50, to the number. So we jump from the syntax to number, for example, to number, or maybe it could be not the number, it could be something else, but usually it's a number because with computers. And that's why the name denotational. So we explain what the expression in the program denotes in another language, and this language is data language. So we assume that there is a meaning already defined, the meaning of some other language, and this language is the language of data. And we explain, and based on this already existing semantic, already existing explanation, already existing meaning, which the reader already has. So the reader already knows what are the numbers. We don't need to explain what is 42 and what is 53. We assume that the reader already has this knowledge. Now our job is to explain how we can jump from our language, from programming language, to the language you already know. So that's why we go from A to D. A is our new language, which we explain you, and D is the language you know. And that's why denotational. So we explain what it denotes. We explain like the blah 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 denotes 55 in your language, in the language you understand. So let's say we try to explain you in English, but you know Russian. So we're going to explain what English means in Russian language. That's denotational semantic. Like in this example, we say x power n is y, where y, and this is the language we assume you already know. So you know how to multiply. You know how to do multiplication of numbers. This is the language which you are familiar with. So we just jump from the expression in our language, which you don't know, to your language. Operational semantic is different. In operational semantic, we describe computation steps taken in order to evaluate the expression to normal form. It means that we say, if on the previous, I like this metaphor with the language. Let's say I'm trying to explain you what, let's say, I'm trying to explain you, yeah, okay. Maybe I'm not ready with an example, but here, look at this, we jump again, it's a different symbol here, so we write it with a different symbol, and it's a mapping from our new language to the same language. So in this case, I'm not moving to the language you know. I don't even assume that you know any languages. I stay in my language. And in using my language, I'm explaining using elements of my language what the syntax means. So it is, if I would explain to you, let's say, what in English means a table. And let's say you know Russian. So in this case, I would say, in denotational semantic, I would say a table maps to Russian word stol. That's it. That's my denotational semantic. And you should understand it because I assume you know this language. That's it. In operational semantic, I would say a table is something with 4 legs and I don't know, and a cover. So I'm staying in English. I don't assume you know any other languages, but I am decomposing my one-word table. I give like computational steps to you. I explain you how you can compute in your mind the meaning of the table. Like use 4 legs and then put the cover on top of them. Oh, you don't know what is a leg? Okay, let me explain you what is a leg. Leg is something which is long, which is thin, which you can put on the floor. Oh, you don't know what is a floor? A floor is something which is horizontal and something which can hold some things on top of them. Oh, you don't know what is horizontal? Now I explain it to you. So this is the operational semantic. I just explain you details, going deeper, but staying in the same language until I get to the so-called normal form. So normal form in this case would be, I don't know, let's say you need to understand some basic things in this English language. Let's say you need to understand what is what is 1, what is 2, what is go, what is jump, what is floor. So some basic alphabet you need to understand. So I will get down to the normal form. I will explain to you what is a table, going into details and explaining until I hit the normal form, until I hit the limit where any further explanation is not possible, and you need to just know it. You need to just have the basic knowledge in this language. So these are operational semantics. So of course, these semantics are easier to grasp visually because you see like the table just immediately jumps to the meaning, but you need to have the meaning. You need to have a second language in which we can explain to you. But in programming it's easy because the second language is data. The second language is data, but not only data, but also the operations on the data. Let's look at this example. I'm saying x multiply. So you need to understand multiplication. So you need to understand that there's arithmetic operations, multiplication. In case of multiplication, it's not so difficult because everybody understands it. But there could be some more complex things. Not only multiplication, there could be something more complex. It depends but usually the languages, are quite simple. So we don't really write languages which have really complex semantic as part of the language. Usually low-level, things which we have in the language, like low-level constructs, they are primitive, quite primitive. So denotational semantic, the first one, is more preferable for faster explanation. But operational semantic is more interesting because it provides the more detailed description of how things should happen, instead of just saying just multiply it multiple times, because this is there's enough intuition should be there. So we just say multiply n times, so people have to just intuitively understand what it is. Here it's more formal. We don't use so many words. We just say x n maps to x with just recursive, inductive description. We recursively define multiplication. Again, we use multiplication here, you see, but it's just only once. And we don't need to say n times, so we don't need to use English word here. So there's no English involved. We just say, oh, yes, we use the if word, okay. But here it was where. So this description is a little bit more formal. And look, this is the normal form. So this is the knowledge we expect you to have. So we say that x is the power 0 is 1. So this is the normal form we get to. So we will explain you the multiplication again recursively until you hit there's nothing to explain anymore. It's just 1, and then multiplications go recursively up. The operational semantics is the specification of an interpreter for the programming language, whereas the denotational semantics tries to capture the mathematical essence of a program, abstracting away from computational details. That's what I told you. So denotational is abstracting away. So denotational, but for me it is easy to understand it with, like I told you, with an example by languages. So imagine denotational semantic moves you to a different language, which is quite rich. So this new language where you jump is also a rich language. It has all the instruments which the reader is supposed to understand. So when you describe your programming language, and if you do it scientifically, if you do it formally, then you will have to use some semantic, either operational or denotational, or maybe both. Sometimes people use both in order to explain to the reader better, to give a better explanation of what the language, how the language works. But you cannot skip that. You cannot make intuitive description of your language if you really want to make something scientific. You need to you need to describe semantic formally, just like showed you before with for example that kind of inference rules. And we will see how to do it with natural semantic separately and operational semantic and the structured semantic. So first is denotational. So remember, denotational is when we jump from our language to the language the reader already knows. And they called natural because this word is coming from the idea that it's more natural to understand this semantic for the people, I believe. So let's look at the example. This is on the top you see my language. The language has 3 commands: faster, stop, and slower. Imagine I'm driving a car. So I'm driving a car and I give to the car 3 different commands. I say go faster, stop, or go slower. So my semantic, I will use denotational semantic. I say this denotational semantic will be defined, will be used, this operator will be used, this relation operator will be used on the domain command, the number will be the speed of the car, so the car is moving with this speed, and we will jump to the answer from the engine and the new speed. So this is the language, my language, and this is the language of the machine, which we already understand. The machine says, okay, I go faster, or the machine says, no, I don't listen to your command. But our language is different. Our language is go faster, stop, or go slower. The machine answers, yes, no, and also changes the speed. So machine says, gives the answer. This is the answer from the machine, true or no, and the new speed. So in the beginning, let's say I go with the speed 20 kilometers per hour, and I tell the machine go faster. The machine says okay, and the speed is, I don't know, 20, 21, for example. So this is where we start. Oh, maybe I didn't write it right. So we start, let's say I tell the machine faster, and it already goes 10, and it tells me okay, and it goes 15. That's the idea. That's how we describe what's happening. This is my starting state of this, my starting situation where I start, and this is where I end. This is my language. This is the number. This is the state. This is my language. This is the state. This is the language which the machine speaks. That's another language. We call it data, and the new state. So let's see the rules which describe the entire semantic of the entire computer which we program. The rule number 1, if I say, it's an axiom. It's not even the rule, it's an axiom. So if I say stop, then the machine immediately says true. This TT means true. So the machine immediately says true, and the speed is 0. Clear. The second rule, if I say faster, and the speed is something, then the machine says true, and the speed goes up plus 20. That's rule number 2. However, the rule has a comment. It's not really a transition on the top, because remember, when you write the rule, it is very strictly that in the inference rule, in the semantic, when you describe semantic, denotational or operational, the transitions must be exactly in the same format, syntactically, on top of the line and at the bottom of the line. So you cannot just freely write whatever you like at the top of the line. any condition. Here I did it, but I did it with the gray color. Probably you see it, it's a gray color, but usually people write it not here, but say if s more than 60 after the rule. But I put it there just to show you that sometimes you can do it, but you need to really mark it that you're not. This is not a formal. You're breaking the law. You're breaking the rule of writing inference rules. So for the inference rule, what's the syntax at the bottom must be exactly the syntax at the top. The syntax of describing this transition. So keep in mind that this is in gray on the top. So I'm saying if I give to the machine the command faster, then it returns me true and goes faster if the speed is below 60. Another rule, if I go fast, if I say faster and it goes with the some speed s, then it tells me false. No, I'm not going to go faster, and the speed is not changed if the speed is already more than 60. So it will just reject my command if it already goes faster than 60 kilometers. The rule number 4, if I say slower, then it will return me true and will go with the speed, which is, it's not going to go below 0, so it's going to decrement 20 from the speed and return me either 0 or the speed, the new speed. And finally, the rule number 5, interesting rule, which says if I give commands one after another, then it will execute the first command and the second command and return me the logical end if both commands were true, and it will and the speed will be changed twice. The first premise is execution of the first command, the second premise is execution of the second command, and they are connected with this s prime. So the s prime, which is going out of the first command, goes into the second command. This mechanism, by the way, was introduced in 1987, the mechanism of describing semantic in a denotational way. And now let's take a look at what this proof tree. Now I want to prove, I designed the machine and I give it to my customer, and I promise to the customer that if the user will sit down on this machine and will say faster, faster, and then slower, and the user started from the speed 45, then I guarantee that in the end the speed will be 45. So it's not going to be over, because look, faster, faster, double faster will be plus 20, and the start was 45 and there's minus 20. So maybe the speed will be, 40 minus 20. So it's going to be 65, right? If you just do the simple math. But I promise and I guarantee, because of my semantic, I guarantee that the speed will not be 65, it will be 45. Why? Because that's how I designed my language, my machine. So there are some limitations, some control points, which will prevent the machine from going over 60 kilometers per hour. How? On my proof tree. Let's take a look. We did it before. So we take this command, we break it down into, we find the rule in our set of rules, which is suitable for this situation. We do it intuitively, and we put this rule here, and this rule has two premises. The first premise is for the first part of the command, and the second one is slower for the second part of the command. So we break it down into two parts. And this part is also broken down into two parts, faster, faster. And these are, they find their own rules in the rule set. So if you want to see the details, let me show you the details. So here we say faster, fast. So I just follow the chain of thought. So I'm saying there's three commands. So they will be executed if these two commands will be executed, and the last command will be executed. These two may be evaluated if this one evaluated and that one evaluated. This one may be evaluated to 65, starting from 45. If we call faster, according to the rule number 2, and the speed 45 is less than 60, then yes, 45 can go up and increase to 65. So this is clean. This part is clear. This part, faster from 65. 65 is copied here. 65 is coming from here. So 65 can go faster. No, false. it cannot go faster, it will stay at 65 because this condition is true. So these two axioms are true. I just proved them. Now, because they are true, this is true. So faster, faster with this 45 in the beginning will lead to 65. I just proved it. This is clear. Next, I need to prove this. So if I go slower, starting from 65, then I will go down and will get 45. Also, I just proved it because I got, sorry, there's a missing line. This is a line, and then R, whatever, I don't remember. R, where is it? R4. So I forgot to draw it. So we have R4, R3, R5, and R5 in the end. So now the whole thing is proved. So I didn't explain it on the, intuitively to you that look, there's an algorithm, like try to use it, write a unit test, there will be a proof, like try to run experiments. No, I formally demonstrated that without the execution of the code, using only the semantic, the formal semantic of my computer, of my language, I show you that you're not going to go faster than 45 in the end. Of course, you will go 65 in the middle, but in the end, it's going to be 45. So let's read the text. The tree is built from the bottom to the top using the rules introduced before. The gray conditions at the top are not parts of the rules. That's why in gray. I explained it before. So they are gray because they just comments. They just supplementary information. Now we get to structural semantic. Structural, or this is operational. They call it structural because they show you the structure of they're based on syntax, and they manipulate with the structure of the code, the structure of you will see it now. That's a second way of, they call structured semantic operation, usually SOS, structured operational semantic. So let's take a look at the program. X equals to X plus 1. The meaning of it may be explained by source rule like this. A equals to E. We just skip it, change the memory. If E goes to N. We already seen that before. It reads, if E may be evaluated to N, then E equals to E inserts a new binding N, a new binding A to N to the state and skips any further processing. To understand the meaning of X plus 1, a new source rule is required. So we don't know how to jump from E to N, because in this case E will be X plus 1. So we don't have a rule to prove to us that X plus 1 can actually be mapped to N. So this missing, the rule is missing somewhere. When you write this rule, and a few other rules, then we have a complete rule set which constitute the operational semantic. This was introduced in 1981. If the natural semantic, they were introduced in 1987, so this was earlier, 1981. So you see, people actually just recently, not so many years ago, people started to understand that there should be mechanisms to explain the meaning of programs. That intuitive description is not enough. And if you see the history of programming languages, then you will see that many languages, they were designed before 1981. Many programming languages showed up in 1970, in 1960. So people were not, at that time, they were not explaining the meaning of code formally. They were just telling each other how to write the code, but without formalities. Nowadays, if you read any paper, any serious paper about programming languages or analysis or compilers or optimizers or refactoring tools, they will all deal with this semantics, these inference rules and the ways of describe semantics. Okay, reduction semantic. Also interesting topic which I want to show you, reduction semantic. So in this case, sometimes it is possible to explain that the program, before starting to execute, may be modified to become simpler. So what we deal with now, up to now, was two different ways, denotational and operational, two different ways of explaining how a program can be executed by the computer. So what the computer will do in order to evaluate the program, step by step. But maybe we don't need to give the program to the computer. Maybe we can modify this program even before the computer starts working with it. So we can reduce the code to shorter code. And that's quite helpful. It may be helpful for the understanding of the code. It may be helpful for the real execution of the code. It may be helpful for a number of reasons. Before you run, you just you just shrink the code and make it smaller. Let's consider quite classic example of reduction, which is coming from lambda calculus. Maybe you know lambda calculus, maybe you've heard about it, maybe you studied it. So in lambda calculus, let's consider an expression. This is an expression in lambda calculus. It basically means, if you look at this is exactly the same, but in Java. So that could be more, for you, could be more, you may be more familiar with this. So let's say you have a function f, and the function accepts the parameter, and it returns itself the parameter. And then we call the function f with the parameter b. So it is clear from here. So we don't need to call the function. We already know the result, it's b. So there's no need to actually compile this code and make the compiler, make the code in runtime to jump into the function, stay in the function, return what was sent to the function, and then assign it to x. We can just instead of this, put b here, and that's it. You see, this is reduction. So instead of explaining that, in our machine, when this happens, then the machine, when it's returned, then it returns the result, and so on, we can just reduce it to a shorter expression. So in lambda calculus, it's called beta reduction. So beta reduction says if you see this code, if you see this lambda xt, then you basically replace this x inside the expression with the s. So whatever you see in the t, whatever is in the t, the x must be replaced by s, which leads us to this. So in this expression, because there's a and a here, so you place b in here and b in here, then you clearly understand that you will return b. Like the same as here. So we're not going to dive deeper into lambda calculus, just look at the Java code. So we make a reduction, and this reduction is described by a rule in lambda calculus. They just say, this is the rule for reduction. So they say, when you see this, let's say we can write a primitive rule. We can say, when you see this, then make it b. Very simple rule. We can make it like Axiom, like this. This is rule number one, reduction rule. When you see that, make it b. Just reduce. And then people say that there is a so-called normal form. So let's say you have an expression, maybe in Java or in lambda calculus, whatever, and then you look, there's a possibility to reduce it somewhere. At this place, remove, like simplify the expression, shrink it to shorter form. Here you can simplify it, here you can a little bit simplify it. But at some point of time you will stop. And there will be no possible way to simplify it any further. It will be just the most simple way. That's it. There will be no possible reduction anymore. So you cannot continue reducing your expression. And that at that point is called normal form. So a normal form is a form that has no more possible applications of reductions. Thus, for example, if you look at this, that's a long expression in lambda calculus. And we use, this is the way you say what you use. So this is the reduction, the so-called beta reduction, which we just described, beta reduction. So I do 3 times beta reduction. I reduce this expression to this, then this one I reduce to this, and this one I reduce to d. This is my normal form, d. So this is basically d, the same as d. So I was just reducing, and I got, boom, no more reductions are possible anymore. And there are questions of how you can prove that that you can reduce, and you will stop at some point. So there is a question in general may exist for formal description of reduction rules, rule sets. The question of terminality. So whether you will terminate at some point, whether you will find normal form for any formula. So let's say you describe this language construct, this language expression, and then you reduce it using a number of rules. That's good. I write you another language construct, and you reduce it again using a number of rules, and you stop. But maybe there is an expression in your language which I give you, and you use your reduction rules, and you will not stop ever. So you will apply. For example, I can give you an example of this reduction rule, which will never stop. Let's say we say, if you see in my language, if you see B and A, then reduce it to A and B. And if you say A and B, reduce it to B and A. So this, if you define these rules, then you will apply them endlessly. You will just change the positions of the two arguments, and they will ever, for example, let's do it more funny. B plus A replaced with A plus B. When you see A plus B replaces B plus A. And then again. It's pretty innocent rule if you look at it just one. Just one rule is pretty innocent. Looks okay. Oh yeah, we have two operands, two arguments. Why not we replace them? And then there's the second one. It's also pretty innocent. It's okay to replace them. But if you do them together, you get a rule set, a rewriting system, which will reduce your expression forever. And there will be no normal form. Because no matter how many times you do it, you will never hit the end, the fixed point. So that's the question. That's the problem. The problem of finding whether your reduction rules, all of them, actually terminate. Whether they terminate for any program. Because if I, for example, send to these reduction rules, let's say this is your reduction rules, and my program is C multiplied by 8. Then none of these rules will apply, and we will say, okay, this is the normal form, because no reductions there. So C multiplied by 8 is the normal form, because none of the reduction rules, and we totally have 2 reduction rules, so none of them apply. Perfect, everything works fine. But I will tell you, look, there is a possibility that I will find you an expression. An expression will look like C multiplied by B plus A. And this expression, you will not be able to find a normal form. You will just, reduce forever. So the question is general. How, by looking at these rules, just by looking at them, without running, without doing the reductions, but just by looking by them, say that for any program, they will terminate. Or for some program, they will not terminate. That's interesting. You can just, it's more like theoretical territory. But if you design your language, and in this language you decide that you're going to use reduction rules, and you will say that expressions in my language may be reduced before they go to the compiler, then you may consider designing a proof of the terminality of your reduction rules. And also another property of the reduction system could be called the property of confluence. So they say that if you, let's say, start from the maybe this is my expression, and I reduce it to another expression, I don't know, something, I can reduce it to another expression using the reduction rule, I don't know, reduction rule 1. Or I can reduce it to some other expression using reduction rule 7. And then I can reduce it here, and then I can reduce it there, and maybe again. So there could be possible different reductions, right? It could be, I can apply different rules, and so on and so forth. So they say that eventually, it will hit the same point. So for this object, for this expression, we have only one normal form. That's basically the essence of this confluence, of the confluence, of the property, the property of reduction, of a rewriting system, confluence. So it always will be will converge at one point. So this will not happen. Like this picture is not possible like this. And stop. This system is not confluent. It means that we can reduce one expression to two different expressions. It could be this or could be that. It's not good in your language. If your language is like that, then I can take your expression and then modify it at the end with two different expressions. Then there are big concerns about the semantic of your language. Like, how come you have two different things? We started from the same thing, but then we ended up with with different things. So maybe they mean different things now. So maybe when we run them, they will produce different results. So the question is, what's wrong with your language if this happens? So you need to prove to me that your reduction rules will always lead me to, even if they diverge, even if they go different directions at some point they will stop at the same point. So for each expression in your language, I will have only one normal form for each. For this one, for this one, for this one, for this, for all of them, I have only one normal form. Okay? This may be useful as well for your future. Okay, I finished with this. In this lecture, I will not show you practical examples because this is not related to code, actually. This is more like theoretical stuff. So there's nothing to code. But maybe you may consider a software which is called COQ. It's quite popular right now. A software for proving automatically the things which I mentioned. For example, prove that your reduction rules terminate, or prove that they converge at one point, or prove something. So you can design your semantic, and then using this instrument, you can automatically feed your rules, inference rules, to this machine, to this software, to this language. It's a special language, and this language will tell you whether your rules, which you defined, your inference rules, actually make sense. So try to just take a look what it is. You need to know that it exists, and maybe you find it interesting for some of your future research projects. We have a number of, we have actually one project right now which is related to this tool. We're using it, starting to use. So if you're interested, you can find me. I can connect you to this project, and you may play with us with this formal automated proof of formal definition of the semantic. So I recommend, I'll send you the slides to the chat, so you can go to the links and find some. Some of them are papers, some of them are video lectures. So I suggest you try to read them and try to watch the lectures. It's going to be helpful. Again, remember that these lectures are not supposed to be detailed formal explanation of everything we're talking, because there is not enough time for that. If you want me to explain your reduction semantics in details with proper examples, then it will take, I don't know, 5 lectures maybe, each for a few hours, and still will be not enough. So there are books about that. So our idea in this course is to give you a high-level overview of what happens, of what exists, and then if you decide to dive deeper, then you do it yourself. You just practice yourself. You try to apply this knowledge to your practical problems, and you will see how it works, because you will learn by doing.